Hi everybody, I'm excited to be here. We'll see, I have both videos and audio in my talk, so hopefully this goes well. And I'm just gonna go ahead and get started here.
I saw changes happening around me that nobody should see happen on a lifetime. Less snow cover, more variability in events, permafrost melting in people's homes sinking into the ground. And I got really interested in climate change. And I wanted to become a climate scientist. And the avenue that took was mapping, looking at trends from satellite data to see, can we see changes? And I, during that time, was also skiing a lot. It's part of the reason why I picked the University of Utah for my undergraduate is the proximity to the mountains, and I probably missed a lot of classes. But I was really interested in the work, and I ended up meeting my graduate advisor, and I told him that I really wanted to study climate impacts on snow. And my first field season, we went out to the San Juan Mountains in southwestern Colorado, which is just a beautiful area of Colorado, and I had skied there before and just fell in love with it. The topography there, there's just jagged peaks, really steep slopes, really amazing backcountry skiing, not that many people. It's pretty remote. And you go out there and you ski and you're basically by yourself. We got to go back multiple times, which is really helpful when you're studying snow because you get to watch it change. And during that season, there was multiple large dust events that deposited on the snowpack, making it darker. Then it'll deposit, it'll get buried again, and then you'll get another dust event, it'll get buried by more snow. There'll be another dust event, it'll get buried by more snow. But then when we went back in May, when the snow was melting, all of those dust layers had combined at the surface. And it's the most dramatic thing I've ever seen. This normally bright white snow, what we think of as this bright clean surface, was red everywhere. It almost looked like soil instead of snow. It was so clear to me then that it was dust controlling the snowmelt timing and not necessarily increases in air temperature. Of course we have warming, but when you have an impact like this, like dust, and we know it's coming from human disturbance, we know it's coming from land use change, you get into this new complexity of it's not just climate change, it's not just warming air temperatures, there's other things going back, feeding back on each other in the system, and I was really hooked. It really hit home how much of our water can come from snow. Like, how could that actually be that we get up to 80% of our water from snow? And when you're up there digging snow pits to the ground and looking at how much snow is actually there, and then looking out all around you and there's snow as far as the eye can see, that's our primary water in the West. And I think at that point I couldn't go back and study anything else.
Okay, so thanks for letting myself introduce myself. The first part of that was missed was about growing up in Alaska and just being really directly impacted by changing landscapes in Alaska, but then being motivated and taking that and applying it to the new place that I live now, which is the Western U.S. And since then, my first season of fieldwork was 2009. And does anyone remember that particular dust on snow season, 2009? Yeah. Okay, some hand raises. It actually was the worst season that we've ever had. So I started doing and studying dust on snow in the worst season that we've ever recorded. And I couldn't go back and study anything else. And I've now been able and fortunate enough to travel the world studying not just dust, but impacts of other light-absorbing particles and the impacts of snow darkening But today I'm gonna talk about, the first place where I started. It's so near and dear to my heart. Just to reiterate what Jeff was saying is this instrumentation site that he now manages and runs, this is the longest running site where we study dust on snow. There's nowhere else like it in the world. It has the most detailed and most continuous observations of dust on snow, both observing when the dust gets deposited, where the dust is in the snowpack, and how much dust gets deposited each season. The observations that are recorded there are incredibly valuable and have allowed me to build a career off of studying the impacts of light-absorbing particles or snow darkening. So I'm going to give you a very sort of high-level overview, and I'm happy to talk about later any of this stuff in more detail. I promise I'm not going to show too many graphs, but there will be a couple in here. I'll try to describe them. So just to take a step back, a lot of people assume dust is a natural aerosol, and that can be true in cases, but we do know now that modern levels of dust are a relatively new problem in the Western U.S. Dust levels increased fivefold following modern settlement of the West, and that's due to land surface disturbance. We just did widespread grazing. We just busted a bunch of crust with all of those animal hooves, and it led to a lot of erosion and dust. What the plot is showing here is actually sort of this low-level background, dust from a lake sediment in a high alpine lake, and then all of a sudden just shoots up, and that's dust deposition levels just shooting up, and then we actually see a slight decline, and that's the enactment of the Taylor Grazing Act. Another thing that we know is that we can get dust from kind of different places, from the west, from the south, but all of our big dust events come along trajectories that are along the southwest, high wind speeds that come over the Four Corners region and southern Colorado Plateau. This is showing back trajectory modeling for dust received at mountain sites in Colorado. So we have a general, pretty solid understanding of where the dust is coming from. So now I'm just going to summarize a decade of work that I have worked on with my graduate advisor, who was Tom Painter, who first established the Center for Snow and Avalanche Studies with Chris Landry. So what we know is that there are no dust-free seasons. Since we've been looking at it, there's always dust. Dust has been observed every year since observations began, and 80% of those dust events occur in the spring months of March, April, and May. Source regions are drying out, wind speeds are picking up. And then each one of those dust events carries a different amount of dust. So the number of dust events we see each season is not related to the amount of dust deposited. And what we see is that seasons kind of tend to fall out into these two categories of typical, sort of background, like that's the dust that's kind of just there, or extreme. And 2009, all these pictures you see of dust on snow are from these extreme seasons where there's sort of this break in the system, and all of a sudden we just get a lot more dust in these extreme dust years. So dust is really, really effective at accelerating snowmelt, significantly more so than even warming air temperatures. Warming air temperatures still impact snow, but we just get less of it because precipitation is falling as rain rather than snow. But during the melt season, it's really the color of the snow that's controlling how fast it melts. And this springtime dust deposition, these 80% of dust events that come in the spring, they correspond to increasing increasing sun. So we have longer days, increasing solar angle, and so that increases the efficacy of those dust events. And then dust is not entrained in melt. Jeff described this. Layers combine at the surface as snow depletes, compounding surface darkening. So we're getting more sun, and the snow is getting darker at the same time. And we know that observed snowmelt rates don't exhibit a relationship with springtime air temperature. We don't see that relationship. In the presence of dust, we see that it's dust radiative forcing, or how much sunlight the dust is absorbing, that controls the rate of snowmelt. So that was that albedo plot that Jeff showed. And we also know, based on future modeling that I've done, that in the face of future climate warming, there's minimal impact from the warming itself on modeled melt timing and magnitude, and it all comes back to the color of snow and the dust. So dust leads, it's not just that it's melting out earlier, it's that it's melting out faster. So it's more rapid and it's earlier melt. This can reduce water yield and can result in forecasting errors. So we know that dust and snow darkening advances snowmelt by a month in those sort of typical years, but by up to 50 days in those extreme years. That's almost 2 months of faster snowmelt. Errors in operational forecasting from the Colorado Basin River Forecast Center have been related to snow darkening impacts in those really big dust years. Dust is not incorporated into their forecasting framework. It's based on precipitation and temperature. So when you have a big dust year, it leads to errors in snowmelt forecasting. And then I'll skip that last one because Jeff already talked about it. And so since I started studying this in graduate school up until now, it's been sort of this accelerated trajectory. There was not much work on it before my graduate advisor and I started working on this. And so basically in the span of 10 years, we were able to go from, well, we don't really know that much about this, to established science. I wrote a review paper on it in 2018. It's now been included in an IPCC report as another impact on accelerated snowmelt past just air temperature. So it's been kind of a wild ride to see how quickly this has made an impact. But I'll just say, like, that, we know the impact of dust on snow, and now it's time to move out and say, what can we do about it? So I'll just, now what we're doing is moving up from the point level. We've made a lot of observations at the point level, snow pits, observation sites, and what my lab is really working on now is moving out spatially. So we have developed a product where we can look at dust impacts on snow from satellite remote sensing. We use the MODIS record, which is a 24-year daily observation from satellite. And we developed a method to retrieve dust impacts and snow darkening from that satellite, which means that every single day we can look at the snow and see if it's clean or if it's dirty. And if we take the average of all of that over the whole Colorado River Basin, that's what this looks like, that middle plot. So those darkest red areas are where dust is most intense and has the longest duration. And we see a latitudinal gradient, which corresponds to where the dust is coming from. So dust impacts are most intense in the central to southern upper Colorado River Basin. And just to give you an idea of what this record can look like, this is a plot where we have elevation by latitude, and this is the evolution of snow darkening from dust over a whole season. So we can watch as it changes over the season as those dust layers come to the surface, where they're coming to the surface, and the amount of impact that that's having. And what this record shows us, this is work by one of my graduate students, what this record shows us is actually pretty interesting. There's a lot of variability from year to year, so we can see in low values and high values across the whole basin. But actually, if we look past over these 24 years, dust on snow impacts are declining across the upper Colorado River Basin. Impacts were more intense in the first decade of the remote sensing record. So some of those really big years, 2009, 2012, 2013, we haven't seen extreme years like that in the most recent decade of the record. And there needs broader context to this. 20 years is not that much time to have an environmental data record. So as we move forward in time, it'll be really interesting to see what happens to these trends. And then just to close up here on modeling and hydrologic modeling, the work that I did previously was to say, okay, let's take data from these towers and build it into a snowmelt model, and then remove the impact of dust and model how clean snow would melt. And that is how we get to the number of days that dust advances snowmelt. But really, if we're talking about operational forecasting, what we want is, one, to move across the whole landscape, and then also, to model what we observe. We want to be able to incorporate dust impacts into our snowmelt model. So this is just a demonstration of a spatially distributed snowmelt model that we are developing for use by the Colorado Basin River Forecast Center, so that they can incorporate dust impacts into their operational water forecasting. And I'll skip through, this is the same area, but what our model is able to do, these green arrows is when there's more energy going out of the snowpack, allowing the snow to accumulate. And so as those arrows are green, precipitation will fall and will stay on the landscape. And then once we get a dust event that's exposed at the surface, you will start to see those arrows turn red. And that means that there is more energy going into the snowpack. And that energy is going to bring the snow up to 0 degrees C and then start melting it. And so we are able to represent this additional absorption of sunlight within our modeling framework, and that actually comes from the remote sensing data. So we've built the remote sensing data into our hydrologic models. And so we're able to account for this within our model, and we're working with water forecasters to incorporate that. And I think this sort of more broadly leads to some opportunities and gaps that we could fill in the future. So the pictures I'm showing observations, and I'll just make the point again, like we've made a lot of observations, and continuing data sets is really valuable. Long-term data sets are really lacking, but we really need to be thinking now about what we can do about it. And I've sort of broken these out into sort of adaptation and prediction and mitigation. So water is adaptation. Like, how do we live with dust on snow now? It's not going away. How can we take these snowmelt models and actually start running them over the whole upper Colorado River Basin and other areas that are impacted by dust on snow? And this is possible now. It's just a matter of resources. Just getting it up in high performance computing, getting it built into systems. We could do this now. But the real question is how to best support informed and efficient water use and decision making by those water stakeholders. And so one vision for this is that we fully incorporate this into the Colorado Basin River Forecast Framework. They provide water forecasts to end users. And this could take, one way that this could look is that we do ensemble forecast runs, basically using the range of dust conditions that we know exist now. And we say, okay, here's the range of possible impacts on snowmelt moving forward. And we would be able to do this on certain forecast dates. So February 1st, March 1st, April 1st, we'd be able to say this is what you potentially could expect into the future. And then more broadly, we just don't understand what's driving the variability of dust on snow at interannual to decadal timescales. We just still don't understand it. I mean, there's some things you have to have high wind speeds, you have to have dry soils, but what drives the difference between those background years and those really big years? And we're teasing out the science, but we don't know enough yet to move towards prediction. And in a given season, if I had my dream, we'd be able to predict what dust on snow impacts could potentially be and incorporate that into our hydrologic modeling to provide that information to the people that can actually use it and benefit from it. And then in terms of mitigation, what I could foresee in terms of snow is we need to define what success could look like. Are we looking for more water, later water? What does that look like? And in the face of climate change, there's some challenges to that. But we need to model these future scenarios to understand what solving the problem looks like. And that might mean different things to different people. And that's why I'm so glad you guys are all here, because I want to hear what if we're able to do this big thing and lower dust emission amounts? How does that benefit us all? What does success look like? Okay, and I will end there.